All right, we're on. So this first initial lecture about the integumentary system, this is our first real system in the human body that we're going to study as an organ system. From here on out, A&P, including A&P2, is just going system by system through the body. So this is our first official organ system of the human body. I'm going to call it my first whiteboard so that we can get going on this. So I'm just going to write integumentary system. I'll switch colors in a minute. Integumentary system. Just so you know, that includes, we always just think of the skin, but it includes the skin, it includes hair, it includes nails, glands, like particularly sweat glands, and some sensory receptors. So I'm going to try to address as many of those things in the next 2 mini lectures as I can. I'm definitely not going to be able to get through all of it today. I'm just going to call up my black pen color because it's easier to see on a white background. I'm going to give you an introductory basic of the structure of the skin, and then we'll get into details of that. So these are just general characteristics, really. It's also called the cutaneous membrane. So if you see the word cutaneous, that means the skin. The term subcutaneous means below the skin. So, for example, if you get a sub-Q injection of something, a medication, that just means under the skin, below the skin. It is the largest organ in the human body, and that means by weight. So we consider it to be the largest organ of the human body, and it consists of 2 main parts, the epidermis and the dermis. The epidermis is basically, I'll go through each layer, but it's 5 layers of avascular epithelial cells. You know that all epithelia are avascular now. And the dermis really is very vascular. So it's vascular connective tissue. And we'll learn exactly what types of connective tissues are located where. This term, just to remind you, hypodermis is also called the subcutaneum or subcutaneous layer. This means below the skin, so it's not part of the skin. So if I ask you, or you were to be asked, what is the true or false? Hypodermis is the deepest layer of the skin. Make sure you say false because it's technically not part of the skin. This is mostly highly vascularized adipose tissue. So I'm just going to write adipose CT. It's very vascular. There's also some immune cells and nerve cells in there as well. All right, so that's just a general overall look at the sections of the skin. Now we're going to get into more detail. So I'm going to put a big number 1 and circle it over here. And we're going to examine the epidermis in as much detail as we have time. So the epidermis is the outermost layer of the skin. It consists of 5 layers. But I want to give you context really quickly. Those 5 layers, so if I were to look at a section of skin under a microscope, it might look something like this. I'm just going to use blue over here. Here's the surface of the skin. And then this is low power magnification on a microscope. We would see this wavy line, something like this. And then we would see a whole lot of tissue extending way down deep. This is just to give you a frame of reference of epidermis and dermis. And it would keep going way off my board as well. Everything up here that I've drawn on low magnification of a microscope is epidermis. Everything in red that I've drawn would be dermis. And the reason I did this was to give you context. Even though the epidermis has 5 layers, all 5 layers are in this very thin part of the skin. The dermis, what we're going to find later, has 2 layers, but they're much thicker, much, much thicker. So those 2 layers of the dermis are 8 times as thick as the 5 layers of the epidermis, okay? So getting back to the 5 layers of the epidermis, when we number them, I'm going to number them 1, 2, 3, 4, 5, just like your textbook, just so you know, at this wavy line that I've drawn to your right, and there's the surface of the skin, we start with layer number 1 down here at the base of the epidermis. So it goes like this. When we number them, they go 1, 2, 3, 4, and 5. So it goes from the deepest layer of the epidermis is number 1 up to the surface, which is number 5. So let me just erase this, and I'll start giving you some facts about those layers of the epidermis. So the first one is called the stratum. Stratum just means layer. Stratum basale. So this means base layer, B-A-S-A-L-E. This is a very thin layer. It's really only 1 to 2 cell layers thick. Most books say 1 cell layer thick. Doesn't matter, the 1 to 2 or just 1. But there are, so let's just take some notes. This is the deepest layer of the epidermis, not of the skin, just of the epidermis. 1 to 2 cell layers. Now, what's very unique about this layer is what's going on in that very thin layer. So I'm going to most likely switch over to a new whiteboard very quickly, but there are basically 2 cell types in this layer. There's a third, but it's kind of rare. There's 2 main cell types in this layer. Those are what we call basal stem cells, which are a form of keratinocytes. I'll explain all of this language, don't worry. So that's the first type, basal stem cells. And the second type are melanocytes. I'll move to a new board where I have more room. So let's just continue that. So let's explain basal stem cells first. At the base of this wavy line, which is the deepest part of the epidermis, we have, I'm going to draw clear, actually white cells in fairly great numbers. Remember, it's not very thick, it's just 1 to 2 cell layers thick. And we're going to just pay attention to those white cells right now. What they do is because they're stem cells, they are continuously mitotic. That means they're constantly dividing, making new cells. So the cells are constantly dividing by mitosis, which is just a form of cellular division. And so they give rise to new keratinocytes. So what I do when I draw this picture on a real board, when we're in person, is I do this. I just draw arrows. So these cells are constantly producing new cells all the time. They're called daughter cells. Okay, that's where our new skin cells come from. Our new epidermal skin cells come from there. So they're constantly dividing, and they give rise to keratinocytes. They themselves are considered, the basal stem cells, keratinocytes, but they're like mother cells, mother stem cells. We also have melanocytes, not in as great a number, melanocytes are also found in that stratum basal, that base layer, and I'm going to draw them interspersed. Really only about, I'm exaggerating the number of melanocytes here. It's about 10%, I think, is the actual comparison ratio. Melanocytes, their sole purpose is to secrete a pigment called melanin. And there's two types of melanin. I'm not sure your book even goes into that much detail, but I'll mention what they are later. So melanocytes secrete pigment melanin, and they are energized by UV light. So when sun rays, UV light, hits those melanocytes, what they do is it energizes an organelle inside of them called a melanosome. And what that does is the melanosome, it converts an amino acid, tyrosine, to melanin, and that's where the pigment melanin comes from. Anyway, this dark amino acid-based pigment, it permeates throughout this layer. So the pigment itself is secreted by the dark cells, the melanocytes, and it not only covers cells in this space, in this area, but it infiltrates inside of the keratinocytes, in the cytoplasm. This is all a protective mechanism. And what it does is it protects particularly the nucleus, the DNA found in the nucleus of these cells, from UV light damage. Okay. So your book also describes melanocytes in great detail. So what I'm going to do now is I'm going to list all cells in the epidermis, but I was getting slightly out of order of your book, which is why I'm cutting to this chase. All cells in the epidermis, just so you have this list, are keratinocytes, melanocytes. Now, you don't really know what keratinocytes are. Now, I haven't described those in detail, but melanocytes for sure. There are also, this next cell is an immune cell that has different names depending on what book you read. I like the term that your book uses. They're called dendritic cells. These are non-specific immune cells. They're just like macrophages. As a matter of fact, I think they have the same precursor monocytes. Dendritic cells are incredibly effective at patrolling just below the surface of our skin and literally engulfing or grabbing any sort of foreign invader, and then what they do is they hold that thing, their capture, off to a lymph node, and they present it to a defense cell like a T cell for destruction, a B or a T cell. So that's what a dendritic cell is. And we also have tactile cells. Tactile, think of sensation of touch. Tactile cells, I'm going to put in parentheses, Merkel cells. So these Merkel cells are actually, they're a bit unique. They're a specific cell, and they're a cell that's attached to a nerve ending. So they're associated with the end of a nerve. They do arise, we do find them in the stratum basal, that deepest layer of the epidermis, but they're really quite rare. They're so rare that I don't even know if any would show up in this diagram I drew up here. All right, so I do want you to recognize this name. This is just named after the scientist who discovered them, but Merkel cells are tactile or touch receptors, and they are real cells that are attached to a nerve ending. So Going back to the stratum basale, these are all cells in the epidermis pretty much. Going back to say a few more things about that deepest layer of the epidermis, I'm going to go to a new whiteboard. I'm going to draw my wavy line here, and everything above the wavy line is epidermis, everything below it is dermis. These stem cells, which are they're keratinocyte stem cells, when they give rise to new stem cells during cellular division, one of those daughter cells typically stays at that base level and continually divides, becomes a stem cell itself, while the other daughter cell either divides again very quickly and or continues to rise to the top. And as the cells get pushed, older cells get pushed toward the surface of our skin, up through the different layers that I'm going to describe to you, on their travels all the way up to the surface of the skin, they die, and they also collect a very tough fibrous protein material called keratin. That's where they get their name. So this term keratin is really just a tough fibrous protein. And as these cells migrate toward the surface of our skin, like I said, they die, they lose their other organelles, and they just collect this stuff. And it becomes harder and tougher as they die and grow toward and migrate toward the surface, or literally get pushed toward the surface. Okay. Before I leave the stratum basale for good, I do want to say something else about melanocytes. So we know that they secrete the pigment melanin, and we know that what energizes them to do that is the contact of UV light or sun rays on those cells themselves. How they produce melanin is UV light causes an amino acid, tyrosine, to be converted to the pigment melanin. And there's an enzyme that enables that activation. So I'm going to put an arrow right here. So this amino acid tyrosine to be converted to melanin requires an enzyme, and it's called tyrosinase enzyme. I'll talk about deficiencies in that enzyme later at the end of this lecture today. So moving on to the next layer, we've talked about this base layer, the stratum basale, very thin, contains the keratinocyte basal stem cells, as well as melanocytes. We described how melanin protects the DNA in the nucleus of all cells around it. Melanocytes themselves are very susceptible to UV light damage. So even though it's kind of an oxymoron, even though their job is to secrete, produce melanin to protect themselves as well as other keratinocytes and stem cells around them, they are very susceptible to UV light damage. You've probably heard of the cancer malignant melanoma. That is literally a cancer of this melanocyte. And now that you know what cancer is, it's just an uncontrolled cellular growth. The fact that if this melanocyte develops a DNA aberration or mutation and it causes it to be cancerous, the fact that it overgrows in your skin is not life-threatening. As a matter of fact, all moles, which is called a nevus, all moles on the surface of our skin are really just an overgrowth, an overabundance growth of melanocytes. It's when these cells make their way deep, not toward the surface of the skin to become a mole, but if those uncontrolled melanocyte cells migrate downward and get into a blood vessel, or a lymph vessel, and they travel throughout the body. This particular cancer, malignant melanoma, likes to set up shop in the brain. So these cells, what they do is they migrate in our body fluids to vital organs, and that's often the case with cancers. It's called metastasis or metastasis. When that cancer metastasizes, it becomes malignant and it chokes off a vital organ. So this UV light is the #1 cause of skin cancers, all types of skin cancers, not just malignant melanoma. So moving on to layer number 2, I'm just going to go back to this board. Sorry, let's go back to the first board. We're still talking about the epidermis and the 5 layers of the epidermis. Just to give you context, we started with this one, the stratum basale. Now I'm going to go to a new whiteboard and talk about layer number 2, which is the stratum spinosum. The stratum spinosum is much thicker than the stratum basale. It's, depending on what book you read and depending on what place on the human body, it's about 10 to 15 cell layers. So it's 10 to 15 times as thick as the stratum basale. The cells in this region are still dividing. So, all right, cells still dividing. That means they are still mitotic, undergoing mitosis, so they are still alive. They're still living. The name spinosum is just a descriptive term that the cells, especially after they have little spikes on them, little spines. That's where the name comes from. These spines apparently don't appear until after we take the tissue out of the human body, so it's unclear whether or not they really appear in real life in a living organism, in a living individual. Nevertheless, these cells are still dividing, they're still mitotic, and they start to produce and accumulate. Sorry about the writing, it's not easy on a vertical glass surface. The protein keratin. The keratin now is accumulating in more mass and is becoming tougher and more fibrous. We also have some dendritic cells present in this layer as well. And just to be specific, it is safe for you to just conclude and remember that melanocytes are found in the deepest layer of the skin, the stratum basale. But in reality, just so you know, some melanocytes may migrate up a little bit into the spinosum layer. Let's go on to layer 3. Remember, we're going toward the surface of the skin. Layer 3 is the stratum granulosum. First, this is a thinner layer. Once again, it's about 3 to 5 cell layers thick. It has some special qualities to it. Really, cells, and what I mean by cells is keratinocytes at this point. They undergo a process of cellular self-destruction called apoptosis. So I'm just going to write undergo. The reason I'm writing this word out is I want you to know what it means. It's a form of cellular self-destruction. You can look it up in any science or A&P book. But to cut to the chase, the cells die and they're no longer alive in this layer and in layers 4 and 5. Also, what's unique about this layer is there's 2 types of granules, which is where the layer gets its name, in the cells. I'm going to try to go in the order of your book. I believe they talk about lamellar granules first. I have an old copy of the book next to me, but I don't have it open. So let me flip. I want to make sure that, yeah, they do mention their, oh, sorry, I went backwards. Well, it doesn't matter. The lamellar granules, so this is just in reverse order that your book lists them, that's all. But they're both just as important as the other. So lamellar granules are granules that the cells produce in this stage, in this layer, and they are glycolipids. The granules are full of glycolipids. Glyco means sugar, lipid means fat. And to be honest with you, it's mostly lipids, mostly fat. But these glycolipids help the skin so it prevents desiccation from drying out. So it holds moisture in, and it's a big and, it sort of waterproofs our skin, keeps moisture from penetrating. So you know that when you go into the shower, you go into the ocean or swimming pool, water doesn't get through your skin to deeper tissues like your muscles and your bones. And it's largely this layer and the production of these granules that really helps with that barrier, that moisture barrier. Second type of granules are called keratohyalin granules. Excuse me. These keratohyalin granules help to form keratin. What they do is it's like they condense keratin for the upper layers. So they really that's supposed to say condense. They really condense the protein keratin into these tight bundles or packages. And this is for, what it does is it makes the upper layers above the stratum granulosum even tougher and stronger. All right, now layer number 4, I'm going to call up on a new board. We're still in the epidermis. So these are really thin layers of tissue. Layer 4 is called the stratum lucidum. Here's the most notable. First, it's a thin, clear layer. Thin meaning probably only about 3 to 5 cell layers thick. So it's a thin, gets its name. Lucid means clear. Its claim to fame is it's only found in very specific parts of the body, on the palms and soles. Also our fingertips. So you can think the palms, the forward-facing part of the hands in anatomical position. So the palms and soles. And we refer to these areas as thick skin because they're subject to much more abrasion and contact than just about any other part of the human body, of the skin. So stratum lucidum, it's a thin, clear layer, and we only find it on the palms and soles. And just to give you a tip, this is also, I'm not going to get to probably all the structures in a hair follicle today. That will be on Thursday's meeting, but we don't find hair follicles on the palms and soles. So it's in the same place. The palms and soles are absent of hair follicles. I'm saying that to help you with one or two of the questions on the using your knowledge exercise that you have been assigned. Okay, layer 5, and the final layer of the epidermis is the stratum corneum. I apologize if I sound really tired today. It's because I was up really, really early, so I am kind of tired. Stratum corneum, this is the outermost, most superficial layer of the skin. It's what you and I can touch when we touch our skin. That's supposed to say layer, so the tiredness isn't helping my spelling. This is a thick layer relative to the other ones. It's typically 25 to 35, these are rough numbers, 25 to 35 cell layers thick. We have basically flat, F-L-A-T, flat, squamous, dead cells that are very tight junctions between them. So this layer is also constantly sloughing off. So we're, I'm just going to say, we shed cells. The number's staggering. It's something like 50,000 cells per minute or something come off our body. Relative to the number of cells on our skin, that's not a whole lot, but 50,000 cells, it's just a constant shedding or sloughing off of this layer, which tells us that we have a constant new supply coming up from those basal stem cells from the stratum basale. So this is constantly working every second, every millisecond of every day. It slows down as we age. And then off the top here, that's this stratum, and you'll see it in pictures of slides. It looks like the layers are literally peeling off because they are all the time. So we have very tight cellular junctions, and its main function up here is protection. That is our outer covering. I'm probably not going to test you on this, but we've all heard the word callus. What a callus is, you and I both know what a callus is from having been alive as long as we have, but really it's an abnormal thickening of the stratum corneum. And that abnormal thickening comes from sort of overuse or from some sort of constant abrasion. Now, this process, I'm going to draw my little layer here, stratum basal layer. Here's a stem cell giving rise to new cells, and they rise up, they flatten, as they reach the granulosum, they die, and they just keep accumulating more and more keratin and becoming tougher and harder and more cornified. And when they finally reach the top, they begin to just slough off. That whole process from here all the way up to losing the top layer of the skin takes roughly a month to a month and a half. But I think the estimate's 4 to 6 weeks is what total new cell growth takes to get from the stem cell all the way up to the surface. There's also something called epidermal growth factor, which is a hormone-like protein that stimulates mitosis in this area, but I don't even think your book mentions it, so you don't have to write that down. All right, I'm going to talk now about the dermis. So let me just call up a whole new set of whiteboards. So before we cut it off today, let's go over. We've talked about the 5 layers of the epidermis. Remember, they're avascular, and all 5 layers are very thin relative to the dermis. So the dermis, there's 2 layers, but they're very thick, especially the second most deep layer. So the dermis is 2 layers. I'll just start by giving you some fun facts or general characteristics. This is highly vascular. That's in contrast to the epidermis. So we have a very rich blood supply. It's made of areolar, dense, irregular connective tissue, which should be familiar to you now. The cells that we find are basically fibroblasts. The living cells mostly are fibroblasts, which you know are immature cells that secrete fibers, and immune cells. I'm going to write macrophages / dendritic cells, but most of the dendritic cells are found in the epidermal region, right underneath the surface of the skin. The dermis resists, it has very high tensile strength, so it resists stress. But it also stretches and recoils. So it's really the dermis that gives our skin its physical characteristics. In other words, mostly how soft it is, how far you can pull it, and how easily it snaps back, how strong it is. All of those features, characteristics are determined by the dermal layers. Finally, before I get into the specific layers, the dermis contains hair follicles. I'll go over these things specifically next time. Hair follicles, glands, nails, and nerves. So it's a whole conglomeration of different things in this connective tissue. Now let's get down to it. Layer number 1 is called the papillary dermis. Now, unlike the epidermal layers, we number, and old textbooks do the same thing, we number the layers of the dermis in the opposite direction. So here's my line between epidermis, here's the surface of the skin. These are 5 layers of epidermis. The 2 layers of dermis down here, we start numbering them from the same place and we go this way. So number 1 is the most superficial layer, and number 2 is actually the deepest layer. So we're going in the opposite direction. Papillary dermis is basically thin. It has thin collagen and elastic fibers. This is mostly areolar connective tissue. There are structures in this area called dermal papilla, P-A-P-I-L-L-A-E, that's plural. If I drop the E, that just means singular. The papillae are finger-like projections. They're just these things that stick up into the epidermis. So these hills that I'm putting arrows under would be called dermal papilla, and that's where this layer gets its name. Papillary dermis are these finger-like projections that go up into the space of the epidermal tissue. I need to just continue. I'm still talking about the papillary dermis here. This layer also contains a receptor called Meissner's, sorry, that's 2 S's, M-E-I-S-S. It's just a person's name. I'm trying to erase my N here. Ugh, too much erasing. That's a U. C-O-R-P-U-S-C-L-E. Meissner's corpuscles. These are basically just corpuscles that act as touch receptors, and they're not cells. So they're not cells like Merkel cells. They are literally nerve endings. So they're the same in terms of function, or they're similar in terms of functions to Merkel cells. They're touch receptors, but they are not actual cells themselves. They're just dendritic endings of nerve cells, and they kind of look like this. This is just a process coming up toward the surface of the skin, and they tend to coil around like that. And they're sensitive to touch, to pressure, to light pressure. All right, the second layer of the dermis is the reticular dermis. And this is the deepest layer of the skin. It's also the thickest layer of the skin. So I'm just going to write deep and thick. It has much thicker and elastic fibers. So it tends to be more strong as well as have even more recoil ability. And they're arranged what looks like haphazardly when we look at them under the microscope, but they do have some organization to them. In general, the collagen fibers tend to run parallel to the surface of the skin like this. It's not a perfect system, but in general, they do. This stuff connects, binds. I'm just going to give you some functions. Connects and binds more superficial layers to deeper layers. It also resists stress and abrasion. So it's really the glue, the thick jelly-like glue that glues all of the more superficial layers that are above it to deeper tissues, connective tissues and connective wrappings around muscles, reticular dermis. So it's rich in blood vessels, so it's highly vascular. I'm just going to write blood vessels. We also find sebaceous glands down this deep. Nerves, hair follicles. That's kind of a misnomer. Hair follicles are actually derived from, so are most glands. They're derived from epithelial tissue, but they dip down deep into the epidermis. That'll become more obvious when I draw a hair follicle for you on Thursday. Most of the glands, I'm going to put comma sweat glands. Those are also called sudoriferous glands, by the way. Now, this junction point between the papillary dermis and the epidermis and these papilla, these dermal papilla that project up, they help create structures called epidermal ridges. So the dermis in conjunction with cells in the epidermis together create true epidermal ridges. So always just think that what they are, they're not actual fingerprints. Fingerprints are what's left from epidermal ridges, but we call them fingerprints. So that's a bit of a misnomer. Your fingerprint is actually just literally a print on a piece of paper or a surface that epidermal ridges leave. So these, as you know, are unique to every single individual. So this pattern that's created like this, especially on thick skin regions of the palms of the hands, the fingertips, and the soles of the feet, we have these epidermal ridges that create a unique pattern for each individual, and it's genetically determined. How do we know that? Because we start to develop these, actually they're well-developed epidermal ridges by the 3rd month of fetal development. So well before we're born, we have these epidermal ridges on our fingers, the arrangement as well on our palms and the soles of our feet and our toes. And they're so uniquely to each individual that even identical twins have different patterns on their fingers. They're unique to every single individual. They also help, these epidermal ridges help with gripping. You and I take that for granted, but when you pick up a slippery a glass of water or any fluid to drink it, well, that's a very slick surface, and these epidermal ridges on your fingertips really help you grip that glass well, as well as all sorts of things. Other primates have these as well, and it helps with their gripping power in like. So we've described what the epidermal ridges are and what they do, and finally this pattern that's created, I'm going to give you another function. It increases surface area. That's really important for functionality in any living system, especially the human body. So I'm going to just quickly go to the next page and expand on the surface area a bit just for a moment. If I draw a line from point A to point B, like that, on my, I don't know how it is on your screen, but on my board, that's about a 2-inch distance. Doesn't matter. If I take the same point A to point B, and I take a piece of string and I wind it like this, and then I stretch that string out, it's going to be 3 times as long as the first line. So that's what increasing surface area does in a living system. It increases the opportunity for things to cross this membrane. So remember, along this line, we've got avascular living epithelial cells right here, stem cells. They don't have a direct blood supply, but we do have capillary networks. They're called capillary loops that penetrate up into these dermal papillae. And by increasing the surface area of this space, we've given more opportunity for things like oxygen and nutrition to diffuse across to these living cells that need that nutrition. So that's the importance of increasing surface area. And lastly, this jigsaw ridge that's created here, if we had epidermis on top of a flat line like this, and we had dermis down here, it would easily separate. Our epidermal layers from abrasion and contact would easily delaminate from the dermal tissue. This sort of interlocking jigsaw really helps interlock those epidermal layers down to the dermis. So it helps with that resistance against abrasion and delamination. Last topic of the day, I promise, is skin color. So let's just call up a new board for that. We're going to revisit the melanocyte thing really quickly and then talk about other pigmentation. There's basically three molecules that give our skin its pigment. By far, and the one that's most influential is melanin. So I'm just going to write melanin. And I've already talked quite a bit about melanin and how it's produced. Just to reiterate to you really quickly, when UV rays hit the melanosomes, let me draw this, oops, sorry, I just knocked my board. Let me redraw this because I will ask you several questions probably about this most likely on the next quiz. When UV light penetrates our upper layers of the epidermis and they hit, if I draw, here's a really big melanocyte. There's organelles in here called melanosomes. Just drawing them dark so you can see them. When the UV light penetrates and hits these melanosomes, it causes that amino acid, tyrosine, to be converted to melanin. And that occurs in the presence of an enzyme called tyrosinase. And then that melanin, as you know, is this sort of fluid substance that secretes out of the cell, blankets the area, and here's a keratinocyte nearby. It also secretes into that keratinocyte and helps protect and blanket that cell's nucleus as well. It can also blanket its own nucleus especially on the surface that faces the sun. But too much UV light can penetrate this cell and damage the nucleus actually quite easily in a melanocyte. There are two types of melanin. I don't think your book goes into this detail, so I'm not, there's actually, so I won't test you on what's not in the book, I promise. But there's something called pheomelanin, which is like a reddish yellow pigment. And then there's eumelanin, which is the dark brown or black pigment. Both of them are energized from UV light, and both of them are created in the same means, meaning with from this amino acid in the presence of this enzyme. I did want to go over really quickly freckles and age spots. What causes those are literally just accumulation of melanin in certain places on our skin. So we get these accumulation of melanin patches. Remember, melanin is just a pigment, a fluid pigment. That's different from a mole. A mole, which is called a nevus, scientific name for a mole. You and I say mole, but the scientific name is a nevus. This is literally an overabundance, an overgrowth abundance of melanocytes, of the cells, not just the pigment. So I'm going to write overabundance of melanocytes. Like I said, when that rises to the surface of the skin and it stops, that's not necessarily a problem. That just creates a mole on the surface of the skin. It's when the uncontrolled cellular growth gets into our fluids and continues to grow and then travels to a vital organ that it really becomes a malignant cancer. All right. So this will help you with your exercises as well. 2 diseases of pigment production. First, albinism. You and I know that when somebody is afflicted with this condition, we call them albinos. This is a description of what it is. It's genetically determined. So I'm going to write it's inherited. And it's the inability of their melanocytes to actually produce melanin. So melanocytes are unable to produce melanin. Okay, that's usually because of the lack of that enzyme, that tyrosinase enzyme that converts tyrosine into melanin. That's the cause. That's very different than something called vitiligo. That's that third eye, there's 3 eyes in that, is long, so it's pronounced vitiligo. This is when there's a loss of cells, so I'm going to write loss of melanocytes in a patch, a particular patch on the skin. It's like depigmentation. In a specific area. This is thought to be an autoimmune reaction. Where antibodies that our bodies produce, antibodies are just little peptides, they're like mini proteins, and they seek out foreign material. Well, an autoimmune response means that our immune cells attack our own good healthy cells. And when you take AMP2, you'll learn why all of our cells, except our red blood cells, have markers on them that identify them as self cells. And that's why our immune cells don't attack them. But in this case, an autoimmune response, it's thought that antibodies actually attack the melanocytes. So it's not a production of melanin like a person who's an albino. lacks pigment in their hair and all over their skin, and they're very susceptible to UV light because of that. That's an inherited problem where the melanocytes are unable to produce the pigment. Vitiligo is an autoimmune response where antibodies actually attack the cells in certain areas on the skin. The other two factors producing pigmentation in skin, other than melanin, hemoglobin, that is the protein in red blood cells that binds oxygen. When that protein in red blood cells binds oxygen, it turns the cell bright red. That's what gives arterial blood a much brighter red color than venous blood, because it has more oxygen in it. Anyway, so vessels, especially in fair-skinned people, vessels that are close to the surface of the skin contribute to skin color, particularly during times of high vascularization. For example, when a fair-skinned person is very hot in temperature, like they're exercising, one of the mechanisms that the body uses to release heat and cool itself is to send blood to vessels near the surface of the body to release heat, so the body can release heat. But that also turns the skin in that person red. So hemoglobin is a contributing factor to skin color, as is a pigment called carotene. Carotene is not made in the body. We obtain it by ingesting foods that have the pigment in it. Carrots, of course, in particular, carrots get their name because they're high in carotene, but also egg yolks have carotene in them, and it's sort of a yellow-orange pigment. And this shows up particularly in fair. By the way, I forgot to say this at the beginning of the conversation. All of us have relatively the same number of melanocytes in our bodies, regardless of the tone of our skin, the color of our skin. The differences in skin color is largely based on how active those melanocytes are. So I'm going to give you an example. My parents were both from Scotland, and very, very fair-skinned people, were very susceptible to sunburn, yada, yada, yada. I have the same relative number of melanocytes as my brother-in-law, who's Greek. He's very dark skin colored, olive skin colored, but his melanocytes are just more active and therefore more protective against UV rays. And it's the story is very close to me because my father actually died of malignant melanoma. So it is, it is very significant. Back to carotene. The last thing I was going to say about carotene is this pigment is a precursor to vitamin A. So we need this in our diets so our bodies produce vitamin A, which is useful for all sorts of things. But too much of it, or I should say an abundance of ingesting carotene, can literally turn the skin sort of a yellow-orange color because so much of it accumulates in the skin. Last but not least, last topic is just a quick few words about tattooing. So tattoos, as you know, it's just the process of injecting ink into the skin. So a permanent ink is injected. It's supposed to be a J, I-N-J, into the dermis of the skin. That's what makes a tattoo permanent. Now that you know, we're constantly making new cells in the epidermis, and those cells are constantly being pushed to the surface, and we lose them. We slough, they slough off the surface of our body. In order for a tattoo to be permanent, it has to be that the permanent ink has to be deposited into the dermal layers of the skin. I've never had it done. My son recently in the past year got 2 tattoos. He said it's very painful. And the process is a needle injects the ink into the dermal layers of the skin, and it peppers the skin like hundreds to up to 1,000 times per minute. So it's really fast, and it injects droplets of permanent ink down into the dermis. The reason it's theorized, I think, that tattoos actually fade is because immune cells start to degrade the ink over time. The cellular activity deep in the dermis, it's thought that immune cells might recognize the ink as some sort of foreign substance and start to break it down. The real way for tattoo removal, of course, is laser treatment, in which lasers are shot into the area. And I heard that's even more painful, by the way, to try to have a tattoo removed. And then the laser actually breaks up the ink droplets, that permanent ink droplets, so that cells in the body can get rid of it more easily and more quickly. And it doesn't, supposedly, it doesn't damage the neighboring tissue around the ink. All right, I'm finished with this lecture, so I'm going to just cut my recording, and then you will be free to ask me any questions you like.